binary heap. So today we will see the operations. Okay. So what is binary heap? Binary heap is a complete binary tree and it should follow the heap order property. So this we discussed in the last class. So in today's class, we will discuss how to insert the nodes in a binary heap and also how to remove the elements from the binary heap. Okay. So let's consider an example of inserting elements in a binary heap. So when you insert elements in a binary heap, we have to ensure whether the tree should maintain complete binary tree structure and also the heap order should be maintained. Heap order property should be maintained. That's an important concept in this binary heap. So here we are going to insert elements like 10, 6, 20, 5, 16, 17, 13 and 2. So these are the elements that we are going to insert now in a binary heap. So always you are going to give smaller values as higher priority. That means smaller values you are going to insert in the root node. In such a way we are going to proceed. Because we know that in binary heap we can maintain the heap order property as min heap and also max heap. Any one property we have to maintain. Now let's start with inserting the elements. So first element is 10. So that element we are going to insert. Okay. So see, first we are going to insert an element 10. So we are creating a node and we are placing an element 10. So next element that we are going to insert is 6. So 6 is smaller than 10. So what we are going to do is, we are going to place the value 6 in a root node. So what we need to do? We need to create a new node and we have to shift the value 10 which is already in the root node to the child node. So 10 should be moved to the child node like this and 6 should be placed in the root node. So now we have inserted two values. First the value 10 is inserted. Next the value 6 is inserted. And we are going to make sure that smaller values should be placed in the parent node. So we are placing 6 in the root node and 10 in the child node. Next we are going to insert 20. So we know that 20 is greater than 6. So already we have 6 in the root node and 10 in the left child. So directly we can insert 20 in the right side. Next node is 5. So we have a tree having two children 10 and 20 and root node 6. Now we are going to insert an element 5. So when you want to insert an element 5, 5 is less than 10, less than 20 and less than 6. So 5 should be placed in the root node. So for that, as I mentioned in this diagram, we have to shift the elements to a lower level so that the 5 can be placed in the root node. So for that, what you have to do? First, you have to create a empty node like this. And we need to push the element 10 to this leaf node. Okay, so therefore we will get a empty node here. Right. Now in this empty node, we want to push this 6 here. Clear? As shown here, see, 6 is there here and 10 is here, 20 is here. And the blank node is placed in the root, right? There we are going to insert the element 5. So we are getting this structure. 5 in the root node, 6 and 10 in the left side and 20 in the right side. Yes. Now we will move to the next value. Next value that we are going to insert is 16. So actually here we are having a tree structure like this, having 5, 6, 10 and 20. So you're going to insert a new node 16. So we know that 16 is greater than 6. So when you compare this particular thing, because the new node that we are going to create will be in this side, because already left side we have a child. So on the right side we are going to create an empty node, and we have to check whether the value that we are going to insert, that is the value 16, is greater than the parent node S. It is greater, so we can directly insert like this. So 6 is the parent node, 10 on the left side and 16 on the right side. And we can ensure that it is maintaining the heap order property. Yes. Now we will move to the next element. So next element that we are going to insert is 17. See the structure? Already we have the tree structure till this. Is it not? Yeah. So for 6 also, we have a complete tree having left child and right child. Now we are going to insert the next element on this side. So here we are having 20 here, you know. So the element we are going to insert here. So create an empty node and check whether this particular value 17 is less than or greater than the parent node. 17 is less. The parent node has 20, it is greater value. So what we have to do? We have to move this 20 down. Yes, and we have to place 20 to this node as shown in the figure here, and an empty node is created here now. There we are going to place 70. Let's see the structure. So this will be the resultant graph. Okay. So 17 here, 20 here. So when you see this complete binary tree structure, we can see that the root node and the parent nodes are having smaller value than the leaf node. Now we will move to the next value insertion, which is nothing but 13. Correct? So already we have a structure like this. So where we want to insert the next element? On the right side of this particular structure. So what we have to do first? We have to create an empty node. And if we place this 13 here, it violates the heap order property, right? Because 13 is less than 17. So what you need to do? How to bring this 17 to this place so that an empty node will be created here. See, this is the diagram. So we need to push 17 here. So an empty node will be created here. In this empty node, the 13 should be placed. Understood? So 13 is here. 20 on the left side, 17 on the right side. Again, we have to ensure whether it is maintaining heap order property. Yes, it is maintaining heap order property. Correct? Now we want to insert the next element. The value is 2. So consider the tree. This is the structure. We have a root node, a parent node on the left side having value 6, and it has a left child and right child. Again, on the right side to this root node 5, we have a value 13, which is nothing but the parent, which has again 2 children. One is 20 and another one is 17. Now we want to insert a value 2. So where we will insert this value 2? Next you have to move to the next level. Correct? So we have to come to this place. So create an empty node down to this 10. And we want to make now this 10 as a parent node. Yes? So this is the empty node created. Can you able to insert 2 here? It's not possible, no? Why? Because 20 is less than. We are going to insert the element 2. 2 is less than 10. So we want to place the value 10 in this empty place. So as shown in this diagram, the 10 will be pushed to this empty node. So a hole will be created here. In this position, we have to, when you try to insert 2 here, is it possible to insert 2 here? No, because when you place 2 here, this particular structure satisfies. But when you compare this with parent, the parent is having the higher value, which is the parent value 6. So 6 is greater than 2. So we should not put 2 here. So what we need to do? We need to push the value 6 to this empty node and make a hole empty here. See this, the next diagram is this side. So 10 in the leaf node, and the next level up, we have to move 6. So what happens? Here we are having a empty node. And we have to check whether we will be able to place this 2 here. Whether it is possible to place this 2 here. When you compare with this structure, it is okay. When you compare, see, 2 is smaller than 6 and it is smaller than 16. So it's possible you can insert here. But when you compare with root element is having higher value than this its child 2, is it not? So what we need to do? We need to push this 2 to the root node. So we want to place 5 in the left side of this child. So 5 will come to this left side, this node, and this node is made empty now. And here we will be able to insert the value what? 2. Okay, so 2 will be placed here. So the diagram, see here, 2 in the root node, 5 in the left side parent, its child, or it has 2 children, one is 6 and another one is 16. And for the 6th parent, it has a child 10. Now just maintaining heap order property, is it not? Yeah. This is about inserting elements in a binary heap. Now we can see how to delete elements from binary heap. So when you want to delete elements from binary heap, we will give higher priority value to be removed from the binary heap. So because there are two things, one is max heap and min heap. So in this example, we are going to remove the value, higher value we are going to remove from the binary. So when you try to delete an element from the binary heap, the node which is having the higher priority will be at the root node. So when you see, finding the value which is at the higher priority, that value, finding it is easy. But when we try to remove that element, we have to ensure that it should maintain complete binary tree structure. That is one thing. Along with that, it should maintain heap order property. So whenever you want to insert elements in a binary tree, or whenever you want to remove elements from a binary heap, we have to maintain two rules. What are the two rules? Complete binary tree structure should be maintained and heap order property also should be maintained. Right? So when you try to remove the higher priority value from the root node, as I mentioned according to this slide, it will be something tedious. So what we have to do, in order to maintain a complete binary tree property, we have to remove the rightmost node at the bottom level. So don't go for deleting element from the root node. Understood? We have to start removing the elements from the rightmost node at the bottom level. So actually what we have to do, we have to create an empty node because we want to remove the value from the root. So when you want to remove the value from the root node, that value should be placed, no? So for that, you have to create an empty node at the rightmost node. And we have to check whether the value should be placed in the empty node without violating the heap order property. If it is not violating the heap order property, then what you can do? You can place the element which is in the root node to the rightmost node, and it's perfectly done. You can remove it. Otherwise, the child with higher priority should be moved up. And this process you have to repeat. And the process of moving this empty spot, that means empty node which is created, no, that you are doing. So that process is called as percolate down. So percolate down is the process that we need to carry out when you delete elements in a binary heap. And when you insert elements in a binary heap, we have to use a process called percolate up. So while discussing about the inserting values in binary heap, no? So the concept that we applied is percolate up. What we did, we tried to remove one, we created an empty hole and we tried to push one element down and the new element is inserted up like that, no? So that process is called as percolate up. So the process that we are seeing in removing elements in binary heap is percolate down. Clear now, students? Now we will move to an example for this. See here, an example is given. This already we inserted elements in the binary heap, no? So the same example I have taken here, having 2 in the root and a left tree and right tree. In the left subtree, I'm having a structure, having a parent node 5 and children as 6 and 16. And similarly, in the right side of the tree, I have 13 as a parent node and 20 in the left side and 17 in the right side. Again, in the left part of a tree structure, I'm having a parent 6, having only one child, 10 in the left side. So from this, I am going to remove an element. Yes. So what we have to do is, according to this percolate down concept, we need a place to put this 10. So when you try to put this 10 at the root node, what happens? Can you able to put 10 in the root node? No, it's not possible. No, it violates the heap order property. So what you have to do? You have to follow the process of percolating down. So for that, we have to create an empty spot. Okay. We have to create an empty spot. See, I have created an empty spot and I moved. Already I am having a value 6 here, right? 6 here, no, because 10 I am going to remove. So 10 when I remove it. So next I have an element 6. So what I need to do, I have to place this 6 in this position. So I am getting a hole here as shown in this diagram. So 6 here, I have an empty hole here and 16 here. So in this particular empty spot, I can place the value 10. So 6, 10 here, 16 here on the right side, left side, and on the right side, 13, its child, 20, and 17. Next, we will move to some gate questions. Okay, so this is about the theoretical part for today's class, and we are going to discuss some of the questions which is related to binary heap about today's topic. Okay, so I have given a graph as shown in this figure. A graph is given. You are asked to find out the curved vertices. What is the meaning of curved vertices? When you try to remove an node, node is also called as vertex. Okay. So in graph we used to call it as vertex. So when you remove any vertex, the graph becomes like disconnected. So such vertices are called as curved vertices. Okay. So in this particular graph, which has some vertices like A, B, C, D and E. So they have given the options also. The options are B and E are cut vertices, C and D, A and E, C and B. So when you remove which vertex, the graph will become disconnected. When you remove the C, there is no connection between E with this part of the graph. Correct. And similarly, when you remove this B also here, when you see here, A and E we have, C and B we have, C and D we have, B and E we have. No? So when you remove which vertices, the graph will become disconnected. When you remove this B and also when you remove C, this part, this particular structure and this E becomes disconnected. Is it not? So therefore, the chord vertices for this graph is B and C. Which is the option for B and C? D option. See here, the answer given is C and B. No. So D is the right answer. Now we will see the next question. A graph is given. We have to find which are the statements is true. G is a complete graph. First option is given as G is a complete graph. Second option, G is not a connected graph. Third, the vertex connectivity of the graph is 2. And the fourth option, the edge connectivity of a graph is 1. So can you tell me which of the statement is true when you see all the four options? Whether G is a complete graph? No. See this diagram? See this graph as shown in this figure? This is a graph G. Whether G is a connected graph? No, because all the nodes are not connected. Is it not? What is the meaning of connect? It's connected, but it is not complete. Why it is not complete graph? There is no connection between all the vertices in a graph. Correct. See here, A is not connected to E and D is not connected to E. So it is not a complete tree. Okay, so they have given G is a complete graph. And second, G is not a connected graph. Whether G is connected graph or not, G is a connected graph. There is a connection between the nodes, no? So G is a connected graph. And the third one is the vertex connectivity of a graph is true. What is the meaning of vertex connectivity? From a particular vertex, we have to see the connection to other vertex. From A vertex, we have a connection to B. And similarly, from A vertex, we have a connection to C. So how many connections are there for A? Two connections. One is here and another one is here. And let's move to another one, vertex B. Is it not? So here, or another one, vertex D. So from D, we have a connection to B and we have a connection to C. So when you see this, the vertex connectivity, after removing the nodes like B and C, again the graph will become disconnected because only these two vertices, B vertex and C vertex, are holding this entire graph. So when you remove this vertex and this vertex, what happens? This particular two nodes will be disconnected from the vertex A. So here again in this graph G, which is the curved vertex, B vertex and C vertex. Clear? So therefore, the vertex connectivity of a graph is 2. That is the right answer for this question. Now we will move to the next question. The given graph is regular. The options given us true and false. A graph is also given. See, this is a graph. What is the meaning of regular graph? So regular graph means all the vertices. That means the degree for all the vertices should be equal. If the degree of all the vertices are equal, then that graph is said to be regular graph. If the degree is not equal, then it is irregular graph. So now we will see the degree of each vertex. So let's take the vertex A. What is the degree of the vertex A? We have to check the connection of, that means the edge which is linking vertex A with other vertices. So A have a link to B, A have a link to C, A have a link to F. So what is the degree of the vertex A? 3. Understood? Now let's go for another one, vertex C. This one. So from C, which are the link we have, or which are the edge we have? From C, we have a link to B. From C, we have a link to the vertex A. And from C, we have a edge to D. So again, the degree of the vertex C is 3. Let's take another one, vertex E. Here. So E is a vertex. From E, we have a connection to the vertex D. From E, we have a connection to B. From E, we have a connection to F. So, from a particular vertex E, there are 3 connections. That means 3 edge moving to another vertex. So, that concept is called as degree of vertex. So, what is the degree of vertex E? It is 3. See, when you see the entire graph, the degree of all the vertices are 3 and it is equal. So therefore, the graph is said to be regular graph. So what is the option? The given graph is regular or not? Yes, it is a regular graph. So the option is true. True is the answer. Now the next one is a graph with all vertices having equal degree is known as dash. The options given: multi-graph, regular graph, symbol graph, complete graph. Already we have discussed what is multi-graph, what is regular graph, what is symbol graph and complete graph when we were discussing about the terminologies in graph, right? So what is the meaning of a graph with all vertices having equal degree? A graph with all vertices having equal degree are known as what? Regular graph. So the option B is the correct. Now let's move to the next question. Let G be a weighted graph with H weights greater than 1 and G dash be the graph constructed by squaring the weights of edges in G. Let let T and T dash be the minimum spanning tree of graph G and G dash respectively with total weights T and T dash. Which of the following statement is true? I repeat the question again. What's given? It's given that there is a graph G and that G is a weighted graph. What is the meaning of weighted graph? Weighted graph means what? In a graph, if we have some weight on the edge, what is the meaning of weight? It is nothing but a positive value that is placed over the edge. And what that weight indicates? It indicates the cost of traversing from one vertex to another vertex. So if we have a graph G having some three nodes or three vertex, you imagine as A, B and C. Assume there is a connection from A to B and the cost for traversing from A to B is 3. So that 3 will be placed over the edge and that positive value 3 is nothing but the weight. So if we have weight in a graph, then that graph is called as weighted graph. And here in this question, the weight on the edge node is greater than 1. They have given all the values are greater than 1. And from the weighted graph G, another graph is constructed. And let that graph be G dash. And how that graph is constructed and what about the weight for that graph G dash? For that, we have to square the weight of edges that are in the graph G. So in a weighted graph G, we are having the weights greater than 1. No, we need to square those weights and we have to place the weights on the graph G dash. Understood, students? And now consider the second part of the question. Let T and T dash be the minimum spanning trees of G and G dash respectively. For the corresponding graph G, a minimum spanning trees are constructed. So let that be T. And for the graph G dash, the minimum spanning tree constructed is T dash. Okay, so T and T dash be the minimum spanning tree for the graph G and G dash. And the total weights, the weights which are assigned on the edge, no, their total weights are assumed as T and T dash, small t and small t dash. So we have to be clear that G and G dash are the weighted graph, where G is the original graph, G dash is the graph which is constructed by squaring the weights of edges in G. And T and T dash are the minimum spanning tree which is constructed. What is the meaning of minimum spanning tree? The subtree which is constructed from the main graph and should not be complete. That is the rule. Okay, you can create many spanning trees like that, and spanning trees will be constructed for the weighted graph, and the sum of weights also will be calculated. In any one spanning tree, the weights will be less when compared to the other spanning tree. No, the weight will be minimum. The sum of weight will be minimum, and that particular spanning tree is called as minimum spanning tree. Understood? So this is the question, and they are asking 4 options is also given. We have to find out which statement is true. See the first option, T dash equal T. With total weight, T dash equal T square. Capital T dash, no? Those two things are what? Minimum spanning trees. Small t, t dash, it represents the total weight. So the first option is T dash equal T with total weight T dash equal T square. Second option, T dash equal T with total weight small t less than T square. Third option, T dash equal not T but total weight T dash equal T square. And fourth option, none of this. Can you tell me which is the correct answer among the 4? When you go through this question, it is easy for us to find out the option. Which one is correct? T dash is equal to T because those two things are constructed from the same weighted graph. What is the only difference? For graph G, the weights, all the weights are assumed to be greater than 1, and the same thing for T dash. For the second graph G dash, it is constructed by squaring the values. Correct. So definitely T dash will be less than T square. So the answer is T dash equal T with total weight what? Small t dash less than T square. So option B is the correct answer. Now we will move to the next question. what is the worst case time complexity of inserting n square elements into an AVL tree with n elements initially? So here we need to consider a tree. Okay, consider an AVL tree where there are n elements initially and you're trying to insert n square elements into the tree, and what will be the time complexity, and we need to find the worst case time complexity. Okay, see, actually the time complexity will be in the order of log n, that we know, right? But we need to find out the worst case time complexity when we insert n square elements. That's the question. So the options they are given as like order of n square, order of n square log n, order of n power 4, and order of n power 3. So which will be the correct answer? Because we know that we are going to insert n square elements, and the time complexity for inserting elements will be in an ABL tree will be in the order of log n. So definitely the worst case time complexity will be order of n square log n. Yes. Next question. Here, this is about a binary tree. So consider a binary tree T which is having some leaf nodes. So the number of leaf nodes given is 200. Okay. So we need to find, the question is, we need to find the number of nodes in a binary tree which is having exactly 2 children. So we know for a binary tree, for each parent, you will be having 2 children. So among the 200 leaf nodes, how many nodes will be having exactly 2 children? One will be the root node, is it not? For remaining, we will be having the parent and its corresponding children. So how many nodes we will be having exactly 2 children? It's very easy question. The answer is 199 nodes. Among 200 leaf nodes, 199 nodes will be having exactly 2 children. Because it's clearly given the tree is a binary tree. Because for binary tree, we'll be having 2 children for each node. And next again, this is also very simple. A tree is given, a binary tree having 20 leaves. 20 leaves is nothing but the leaf nodes. The number of nodes in T having 2 children. So the same thing, in the previous question we have discussed, a binary tree having 200 leaf nodes. Here it is just 20 leaf nodes. So they have asked the question, the number of nodes in T having exactly 2 children. Among 200 leaf nodes, the nodes which is having exactly 2 children is 199. But here in this particular example question, we have only 20 leaf nodes. So number of nodes in T having 2 children is 19. And now we will come to the next question. Let H be a binary min heap. So this is a binary heap where we are focusing on min heap property. Okay, it's a binary min heap consisting of n elements. The number of elements is represented as n having n elements implemented in the form of array. So it's very easy. The binary heap, we can represent a graph in the form of like adjacency matrix, adjacency list, like that we can represent, right? Similarly, binary heap can be implemented in the form of array. That is an important note. So here we are having n elements and which will be implemented as an array. The question is, what is the worst case time complexity of an optimal algorithm to find the maximum element in H? H is a binary min heap. What is the worst case time complexity of an optimal algorithm? So, as we know, when you come to the case of a min tree, we need to find out the maximum element. And in min heap, always maximum element will be in the leaf node. Which element will be in the parent node and root node? High value. Okay, sorry, min heap, right? So in min heap, in root node will be having the less value, that means lowest value. Then its parent nodes we are having, no, that also will be having the low value. And which nodes will be having the higher value in the leaf node. So this heap order property is called as min heap. So it means that in min heap, the root node and the parent nodes will be having smaller value than the leaf node. Right. So in worst case, we need to search till the leaf node, because leaf nodes are having the maximum value, no? Yes or no? Yes. We need to focus till the leaf node, because the maximum element will be in the leaf node in min heap, in min binary heap. Our question is what? We need to find the time complexity of an algorithm to find out a maximum element. So in binary min heap, the maximum element will be in the leaf node. So we have to perform searching from the root node till the leaf. So can you be able to perform binary search here? No, because it is not a binary search tree, is it not? It's a complete binary tree. So it is not a binary search. And heaps need to be in a sorted order. Correct. So what will be the case? So the worst case will be like n by 2 plus 1. Correct. So here what is the case of worst case time complexity? Order of n. Order of n. So which is the option for order of n? This option number C. Is it not? So the answer is order of n. So what is the worst case time complexity of an optimal algorithm to find the maximum element in H? It is order of n. Now we will move to the next question. So consider the following statements. The first option, that means four statements are given. First statement is the smallest element in a max heap is always at the leaf node. Smallest element in the max heap is always at the leaf node. Second statement, the second largest element in a max heap is always a child of the root node. Third statement, a max heap can be constructed from a binary search tree in order of n time. Fourth statement, a binary search tree can be constructed from a max heap in order of n time. So four statements are given. Which of the above statements are true? Among the four statements, which of the statements are true? The four options is also given. So we have to go through each statement. The smallest element in max heap is always at the leaf node. Whether it is true or false, it is true, is it not? In max heap, always smallest element will be in the leaf node, and root node and parent node will be having the higher value. So first option is correct. Now we will move to the second option. Not second option, second statement. Okay. The second largest element in a max heap is always a child of the root node. See, the second largest element in a max heap is always what? The child of a root node. Exactly. Then which one is the first largest element in a max heap? Anyone? Which is the first largest element in a max heap? It is just nothing but the root node value. Okay, so therefore, the second largest element in a max heap is always the child of the root node. So second option is second statement is also true. Come to the third one. A max heap can be constructed from a binary search tree in order of n time. Exactly. We can construct a max heap from a binary search tree in order of n. So that is also the correct statement. And come to the fourth one. A binary search tree can be constructed from a max heap in order of n. Statement is true or false? It is false statement. It's not possible for us to construct a binary search tree from a max heap. It's not possible for us to create. So the fourth option is false. Okay. Now we will move to the next question. An operator delete of I for a binary heap data structure is to be designed to delete an item in the ith node. Assume that the heap is implemented in an array and I refers to ith index of an array. If the heap tree has depth d, then what is the time complexity to refix the heap efficiently after the removal of an element? So we are having an operator delete. So the operation need to be performed is delete operation for a binary heap data structure. Okay, and we need to delete an item in the ith node. And assume that the binary heap is implemented in array concept. So there I refers to what? Ith node refers to ith index of an array. And the depth of the tree, heap tree or binary heap is assumed as D. Then we need to find out the time complexity to refix the heap efficiently. When you remove an element, after that again we need to refix. No, we have to maintain the heap order property. And in that time, what will be the time complexity? The time complexity is what? Order of D and not it is order of 1. That will be the time complexity. Now we will move to the next question. Consider a max heap which is represented in an array. So a heap is represented in an array having values like 40, 30, 20, 10, 15, 16, 17, 8 and 4. So the array index value, that means the index position is also given and the corresponding value is also given. So in index 1 we are having a value 40, in array index 2 we are having a value 30. In array index 3, we are having the value 20. Array index 4, we are having the value 10 like that. And now we are going to insert an element. Okay, so consider we are going to insert a value 35. So after inserting an element 35 in this binary heap, what will be the new heap? What will be the array value of a new heap? Here also 4 options are given. You need to find out where this 35 will be placed. It's very easy because the array is here the heap is represented in the form of what? Array. So we can easily find where we have the value 35. So when you see all the 4 options, the second option, that is option B, holds good, like 40. Then after that we have 35. Yes, so 40, 35, 20 and again 10. Then we will be having the value 30 and then 60, 70, 8, 4 and 50. Okay, so option B is the correct answer. Now we will move to the next one. Consider a complete binary tree where the left and right subtrees of the root are max heaps. So we are considering a binary heap. So we need to say check with what? A complete binary tree. Where the left and right subtrees of the root, they are nothing but the max heaps. And the lower bound for the number operations to convert, we are going to convert the tree into a heap structure. When you do that, the number of operations that we are doing, what will be its value? Will be the value of sigma log n or simply n or simply n log n or n square that we need to find. So normally when you traverse a tree and when we convert the tree into a heap, the value will be log n always. So the answer is log n. And next, we are going with a question on priority queue. Yes, exactly, because the main application of binary heap is implementation of what? Priority queue. See, a priority queue is implemented as a max heap. Initially, it has 5 elements. The level order traversal of a heap is 10, 8, 5, 3, 2. 2 new elements 1 and 7 that you are going to insert into this heap in that order itself. Already we are having an order, no? In that level order itself, you are going to add it. The level order traversal of a heap after the insertion of the elements. Again, 4 options are given. So initially we have a heap having the level order is 10, 8, 5, 3 and 2. And we need to insert two elements 197. Where this 197 will be placed? After inserting the values, what will be the level order? That we have to find. Understood? So how we have to insert the values? 8, 10, 8 is there. So we want to insert the elements, what? 7. Correct? So that can be inserted after 8, 7 can be implemented. Then after 7, between 8 and after 8 already we have 5. So in the middle we have inserted 7. Now we want to insert the element 1 also, where we need to insert. So after 7 we will have a value 3. Next we will have a value 2 and then 1 and then 5. So the level order of traversal of a heap after inserting the elements 1 and 7 will be 10, 8, 7, 3, 2, 1 and 5. So option A is the correct answer. So next question. A max heap is a heap where the value of each parent is greater than or equal to the value of its children. Okay, so max heap means what? Value of the parent will be greater or equal to the value of its children. Which of the following is a max heap? So in this 4 diagrams, 4 heap is given. Options at the heap is given. Which one will have the greater value in the root node and the parent node? Only see here. What about? We have to see A option is also having higher values. But the thing is, it should be a binary heap. What is a binary heap? It should be a complete binary tree and also it should maintain heap order property. So two properties we need to satisfy. Then only it will be a binary heap, either min heap or max heap. Here it is a max heap. So value of each parent should be greater than or equal to its children. So like in such a case, which option will be the correct one? Second option, that is option B, because see here in max heap, see the parent, which is nothing but the root having greater value 10. Next greater values 8 and 6, which is placed in the parent node for this tree and this subtree. And child nodes or the leaf nodes are having lower values. But here see the C option, it is not like that. See 10 is here, here we are having 5 and 8 is here, so it is not a correct answer. This is also not the right answer because we are having 10 here. 10 should be in the root node because it is the highest value, no? According to max heap, the value in the parent and root node should have greater value. Okay. So this is all about for today's class. I hope you enjoyed the class. You understood? You enjoyed? So again, we will meet you in the next session. Okay. Thank you all students. Bye.